Very good. So then let's start. It's a pleasure to introduce today's speaker, Patricia Ribes-Metidieri. Patricia got her physics degree at the University of Barcelona and then joined the master program at the Ludwig Maximilian University in Munich. After that, she started a PhD at the Radboud University in Nijmegen, the Netherlands, and defended her thesis 3 months ago. She's now a visiting researcher at Louisiana State University. And next month, she's taking up a postdoctoral position at the University of York. And today she's going to tell us about entanglement creation or not creation of entanglement in local observables during inflation. Patricia, the floor is yours. We look forward to your talk.
So first of all, let me thank you for organizing this and for giving me the opportunity to sharing my work with you. So as Albert was mentioning, today I'm going to try to convince you that inflation does not create entanglement in local observables. What I'm going to talk about is based on this paper that you can search here in the archive, which it's a work done in collaboration with Iván Agulló and Beatriz Bonga. So this is the plan for the talk. I will first start to give a motivation of what I'm going to talk about and why should we care about this entanglement. Then I will give some details about the framework I'm going to work on. Then I will give some brief examples in Minkowski spacetime just to clarify some aspects. And finally, I will give you the main results that I want to talk about today about entanglement in de Sitter spacetime, followed by some brief conclusions. So let me start by telling you what this talk is going to be about. So in a brief word, this talk is going to be about entanglement in quantum field theories. And in particular, I will be interested in trying to learn about some aspects of how this entanglement is distributed. So why should we care about this? Well, there are many reasons why you would care about entanglement in quantum field theories, ranging from the most operational, so how to extract it, to the most fundamental. But in this case, I would say, well, you should at least care a little bit about entanglement because it is everywhere in quantum field theories. And this is the result of a well-known theorem, the Ribes-Metidieri theorem, which just as a brief recap, so consider a pre-Hermitian scalar field in Minkowski spacetime, and let's denote by this get the Minkowski vacuum, and by sigma a Cauchy hypersurface. Then you know that we can define finite norm operators in our theory by smearing the operator valid distribution phi with a function f compactly supported in an open neighborhood of our Cauchy hypersurface. What is also reasonable is that states of this form are sufficient to generate the whole curved space of our theory. What is not so reasonable at all is the content of the Ribes-Metidieri theorem, which essentially tells us that this last statement, in fact, that these states are sufficient to generate the whole Hilbert space of the theory, is also true even if we restrict these functions, all the possible functions in this state, to be supported in an arbitrarily small neighborhood, open neighborhood of our Cauchy hypersurface. Now you think about this is quite surprising, right? Because it tells us essentially that we can create any state, in particular a state with support arbitrarily far away, by acting on the vacuum with local operators. And the reason why this theorem, or the reason behind this result is often interpreted precisely as being due to the entanglement structure of the vacuum. So entanglement is ubiquitous in the vacuum of a QFT. Now, of course, this theorem also has some limitations because even though it tells us that there is entanglement, it doesn't tell us how much or what are the operators, if you want, that are entangled. So basically, given two space-like separated regions of spacetime, such as this one, if you try to find all possible operators locally supported in region A and all those in region B, which ones of these are entangled and by how much? So in practice, answering these questions is quite hard. I think This is something we all agree. And while there are many different approaches to try to understand how entanglement is distributed in quantum field theories, my goal today is not to review these approaches, but to present a complementary approach that will help us to understand some aspects of entanglement in quantum field theory. Again, it will have some advantages, as I will show in a few minutes, but it also has some limitations. This approach is based on some previous literature that you can find here. Now, the main idea behind the approach I'm going to present is a relatively simple physical idea, which is that most of the complications in understanding entanglement in quantum field theories stems from the fact that quantum fields pose infinitely many degrees of freedom. And that's true even if we restrict to a field in a certain compactly supported region of space. However, in practice, if we want to extract some properties of a certain field using, for example, a measuring apparatus, what we find is that, well, we are limited in how many degrees of freedom, how much information of the field we can extract. As I am representing here pictorially, if we want to measure some properties of a quantum field with a detector that's made of a finite number of pixels, and it's measuring for a finite time and at a given temperature, a given energy, what we are going to end up with is not all the possible information of the field, but rather, let's say, smeared or blurred image with n bits of information. So the framework I'm going to present is based on this idea of truncating the degrees of freedom of a field that we can access based on this, let's say, physical motivation. Plus, I'm going to use the Gaussian formalism, which means I will be dealing with Gaussian states and free evolution. Now, the reason behind this is that we can construct a framework that has some advantages. In particular, we are able to avoid ultraviolet divergences that typically plague quantum field theories, since the algebras of observables that we end up with are von Neumann type 1 algebras, and so mathematically essentially the same as quantum mechanics. Since we are using Gaussian states, we can compute the reduced states for our finite dimensional subsystems. We can also use all techniques and results from quantum information. And finally, we are still able to retain some features of the full quantum field theory. For instance, as I'm going to explain later in more detail, all reduced states that I'm going to compute using these techniques are going to be mixed. And this is a consequence of the entanglement structure of the full vacuum of quantum field theory. Of course, this approach also has limitations. The first one, as I was saying, by construction, is that it's limited to free theories and Gaussian states. However, as I will explain, there are some physically interesting situations where this is all we need. But the second and most important limitation is that basically we are forced to focus on finite subsets of degrees of freedom, when we know that, well, a quantum field has infinitely many of them. So if we have some results for a finite set of degrees of freedom, how do we know whether this applies to another set of these infinitely many sets we could choose? So in order to alleviate this second limitation, what I will do is that I will focus on universal properties, meaning that they apply for any subset of degrees of freedom that I will choose with a certain, within certain choices. And this leads me to the second goal of this talk, which is going to be understanding entanglement in the cosmological patch of the Sitter space. The main reason for this, why we are interested in this, is because we are going to use it as a toy model for inflation. And the results that we are going to derive, or that I'm going to discuss, are actually interesting for cosmology. So, as you know, we believe that there was a period of accelerated expansion of our universe called inflation, during which the perturbations of the inflaton and curvature fields, these perturbations were stretched over cosmological distances by the cosmic expansion. And these perturbations later on give rise to the seeds that generated the whole structure of our universe. So what we want to understand better is how much entanglement is generated at the end of inflation between local observables using these tools. Now, I would like to continue by giving you some more details of the framework that I'm working on. And to this, let me first tell you what the setup is. So consider globally hyperbolic manifold, or globally hyperbolic spacetime with a metric G and foliated using Cauchy hypersurface sigma. Here, we're going to consider a free Hermitian scalar field described in the canonical formalism. So instead of working with our operator value distribution phi on the form manifold, I'm going to describe the field using this tuple of field and momentum on a given Cauchy hypersurface. Then let's further assume that we can build our typical Fock representation of the quantum theory, which is going to be described by these three elements that are going to be important later on. So I would like to make them explicit. First, a quadratic form in the phase space that induces an inner product and which is associated with the vacuum state of my theory. In Minkowski spacetime, that would be the Minkowski vacuum, and in the case of the sitter, I will look at the Banach-Davies vacuum. Then I'm also going to consider the Cauchy completed version of the phase space, of the classical phase space of the theory, Cauchy completed with respect to this form, and complexified. And
I'm not sure whether it's a problem from my side, but have we lost the
finally,
speaker?
a symplectic form. Yes.
Patricia, I don't know if it was just a problem from my side, but for like maybe half a minute or so, we couldn't hear you, or at least I could not hear you.
I couldn't either.
So maybe you
Okay.
can go through again the Fock representation and just because we might have, I think we might have missed that explanation, the second half of this slide. There was a problem with the audio.
I apologize. I think my connection is not the greatest. Please let me know as soon as something like
So
this
far,
happens.
everything was fine except for this half a minute where we lost you.
Okay, no problem. So as I was saying, we also assume that we can build a Fock representation of our quantum field. And this Fock representation is going to be, well, basically the which gives rise to an inner product and which is associated with the vacuum. In the case of interest, it's going to be associated with the vacuum of the Fock state, of the Fock representation. Then I'm also going to consider the complexified and Cauchy completed version of phase space, where I'm Cauchy completing it with respect to this inner product. And finally, a symplectic form, which is defined in this Cauchy complexified phase space and acts as usual on elements of this phase space, which you can see here. Finally, I'm just noting that I'm going to be using natural units throughout this talk. Now, an important ingredient that I'm going to be using in what follows is that of linear Smith operators, which I'm going to be defining as the contraction of the symplectic form, or the symplectic form acting on elements of this complexified Cauchy completed phase space and this tuple of field and momentum operators. where you can understand each of these elements in the phase space as a tuple, as a pair of functions, essentially. Which, for the time being, since we are interested in local observables, we are going to consider to be compactly supported. Now, this is perhaps a bit of a fancy way of simply writing something we are very familiar with, which is essentially a smear version of a linear combination of field and momentum operators. Moreover, I will be referring to a single degree of freedom of the field as follows. So, given any two of these linear smeared operators that are non-commuting, I will say that the algebra they generate is what defines a single mode or a single mode subsystem of the field. Now, up to this point, you might be thinking, well, this is just, a relabeling of things that we are very familiar with. So why is this even interesting? Why do we bother to do this? And the answer is that this kind of formalism that I'm introducing is going to allow us to describe or to establish a direct connection between the way we understand quantum subsystems and classical ones. In fact, when we talk about quantum subsystems, what we understand is that we are talking about a subalgebra of observables. While when we describe or we discuss classical subsystems, we usually understand by this some symplectic subspace of the phase space of our system. So this language allows us to establish a one-to-one correspondence between the two. And the reason why this is interesting, as I will be explaining in a bit, is that it will allow me to essentially discuss quantum subsystems and also, thanks to some of the simplifications I'm doing, correlations in the quantum system in the language of classical subsystems and symplectic geometry. Now, in principle, we can do this for every possible linear system or for every possible linear observable on a space that is infinite dimensional. But remember that what we are going to do is we are going to focus on finite dimensional subsystems. So on subspaces that are finite dimensional here. And as I was mentioning, we are also focusing on Gaussian states, which in the language of symplectic geometry are states that can be completely and fully characterized by two things. One is a covector in phase space, which is defined by the expectation value of each of these smeared operators. And second, a two-covariant tensor in phase space, which again is characterized by this sigma, which is given by the symmetrized expectation value of any two smeared operators, where this hat here defines a centered operator, defined like this. This sigma here is what we call the covariance matrix of our system. Now, before I continue, I need to introduce one further ingredient. In particular, I need to talk about complex structures. So in this case, we are going to use that the symplectic form has an inverse in this complexified Cauchy-completed phase space, which allows us to define a linear automorphism defined like this in this phase space, and which for pure states like the vacuum, which is what I'm going to be focused on mostly, satisfies this condition. So the application of this map twice gives minus the identity. This map defines a complex structure. Now, as I was mentioning, in the rest of the talk, I'm going to be focusing on finite dimensional subsystems. And so I'm going to essentially restrict this complex structure for these finite dimensional subspaces. This procedure gives rise to a restricted complex structure, which has very interesting properties. In particular, its spectrum is of this form, where each of these mu y are positive numbers larger than 1 and are called the symplectic eigenvalues of the reduced complex structure. or the reduced, the symplectic eigenvalues of the associated covariance matrix. And of course, for the restricted symplectic, for the restricted complex structure, there is this inequality that is satisfied where the equality where the equality applies when all of these numbers are equal to 1 and the reduced state is pure. Now, this is important because, as I will say, all the relevant information in our Gaussian state law is encoded in these sets of numbers. So essentially, I can describe my Gaussian state or my Gaussian reduced state in terms of just these n numbers, these symplectic eigenvalues of the covariance matrix. And what do I mean by all the relevant information? In particular, this is going to allow me to talk about correlations and entanglement. Let's see how. So consider two finite dimensional subsystems of our Cauchy-completed complexified phase space. Then we can define the von Neumann entropy of each of the reduced states in system A and B using a very simple formula, which is essentially the application of this function, this simple function, on the n symplectic eigenvalues associated with each of these two subsystems. And if we want to describe, we can also describe from this mutual information, which, as you know, gives us a measure of the total correlations, in this case, between my subsystems A and B. Again, using this simple formula. Now, the problem is that now, as I was mentioning, the reduced states that we are going to find will be generally mixed. So essentially, von Neumann entropy is no longer a measure of entanglement between two such subsystems. So instead, we have to do something else. And this something else, the way we are going to measure entanglement is using the logarithmic negativity, which is defined as the trace norm of the partially transposed density matrix for the reduced system AB. Now, as I was mentioning for Gaussian states, this quantity can again be measured in terms of a simple set of numbers, which in this case are the symplectic eigenvalues of the partially transposed state. Now, why do we focus on logarithmic negativity? Well, because of this thing has very interesting properties. In particular, logarithmic negativity larger than 0 is sufficient condition for entanglement. Moreover, this is an entanglement quantifier that is valid for mixed states. And as I was mentioning, all reduced states we will be working with are essentially mixed. And finally, because this quantity is necessary and sufficient for partitions of 1 versus n modes, which are essentially the ones that I'm going to be talking about. So I know that this is all a bit abstract, so as a next thing, I would like to show you an example of how to compute some of these things in Minkowski spacetime in the most simple example that we can consider. That is a single mode subsystem in a massless scalar field. So consider a pre-massless scalar field in the Minkowski vacuum, and we're going to build a single degree of freedom of the field by choosing two elements of the complexified phase space, given, for example, by these functions. Where these functions here are defined in this way, you can see a figure or a plot of these functions here, where this A is a normalization constant, and these are compactly supported in a compact region, in particular in a sphere. Now, the subsystem, what we will call subsystem A, is basically the span or the subset from the symplectic subspace made of the span of these two vectors. And this is a subsystem of the full Cauchy completed a complexified phase space. Now, an interesting thing to note here is that these functions are not infinitely differentiable. In fact, for this parameter delta equal to 1, this function is only continuous here. And the reason is that this phase space is actually larger than the classical phase space of the theory. And if we want to compute these operators, which we can do again as smeared operators, what we will see is that, well, essentially they satisfy canonical commutation relations, so that the reduced symplectic form takes a very simple form. It's very simple, it's just this matrix. The mean is 0 in the Minkowski vacuum, and the covariance matrix is given by this simple form, where these objects here are defined by Sobolev inner products, in this case of indices -1/2 and 1/2. This will be important later on in the case of Schwarzschild of the zeta spacetime. Now, as I was mentioning, these functions do not need to be infinitely differentiable. These functions need to be part of a Sobolev inner Sobolev space, which essentially corresponds to the enlarged phase space of the theory. Now, for the entanglement of the zeta spacetime, in this case, I'm going to be talking about the cosmological patch of the zeta spacetime, which is described by this metric, where this A is the scale factor and it as the cosmological time ranging from -infinity to infinity. Again, we will be talking about particular Cauchy slices of this spacetime. And here, I'm going to consider local observables. That is, given a free scalar field in the zeta spacetime in the Davies vacuum with a small mass, given by which I'm going to parameterize with this parameter mu, and I'm going to consider observables that are compactly supported in a region of radius r, which is large compared to the Hubble radius, as I will explain later. Now, again, the types of observables that we can consider are essentially labeled by elements of the phase space, but for simplicity, I'm going to consider elements that are of this form, which gives rise to smeared field and pure smear momentum operators in this case. And remember again that, I'm going to consider that F and G, yeah? Is there a problem? Can you hear me?
Yeah, no problem. It was just a quick question, but finish your slide. I'll ask when you finish the slide. It's just a small detail.
Nice. For simplicity, I'm choosing in this talk operators of this form. And I'm also going to choose the normalization of these functions that these two operators satisfy canonical commutation relations. And as I was mentioning, remember that the algebra generated by these such observables is what we are going to call a single mode subsystem. Yes, other questions?
Yeah, just a short clarification. I'm not sure you showed that on the previous slide, but with this choice you have here, so this would be for minimal coupling to the curvature. So m = 0 would be massless minimally coupled limit, or?
Yes, that's correct.
Okay.
So yeah, we are considering a massless a massive minimally
coupled. Okay.
Coupled field.
Thanks.
Yeah.
Mm-hmm.
But with a small mass.
Thank you.
Okay. So again, since I want to study correlations, what I'm going to look into the most simple two-mode subsystem that I can consider, which is essentially given by this kind of situation. So two single-mode subsystems that are spacelike separated from each other. So as I mentioned earlier, what we are doing, or the simplifications we are considering, allows us to describe the reduced state of such two-mode subsystem in terms fully of the covariance matrix. Because remember, the Davies vacuum is, well, a vacuum, so that the average of the mean of the first moments of the field vanish. And so essentially, if I know the correlations between these two-mode subsystems and the self-correlations of each of these, I can describe the whole properties of the state. So one of the main points in this talk is essentially see how we can define or how we can describe these correlations. And when we do this in this limit that I was talking about, so essentially for a field of a small mass, when it is supported in a large, in a region that is large compared to the Hubble radius, then we find that these correlation functions can be described in a relatively simple manner. In particular, we find that they split into two terms. The first one, which is the same contribution we find in Minkowski spacetime, again, where this is a Sobolev inner product. And the second one, that depends here on the curvature through the Hubble radius, which is also described in terms of a Sobolev inner product, in this case, with another, with another index. Now, this term is the one responsible for the well-known infrared divergence of the Davies vacuum for massless fields. So basically, this thing will in general diverge when mu goes to 0. Plus some additional terms which are subleading in this limit. We can do the same also for the momentum-momentum correlations, and we find that the first contribution is essentially the same we find in Minkowski plus some subleading terms, and the same for field momentum correlations, where we find, in this case, one term that vanishes in the limit when h goes to 0, so in the Minkowski limit. Again, as you can see, this has a relatively simple structure in terms of these Sobolev inner products, which are defined like this. And why this is interesting is because, well, essentially, I'm not saying, or what follows, I'm not going to say what these functions are. So I'm going to essentially try to analyze what happens or what are the correlations between any two such subsystems. And so the key in order to do this is precisely to use some well-known relations between Sobolev inner products and norms. So all the complication that we had before is going to be encoded now in this, in trying to understand, in trying to understand how these correlations act without having to specify what these functions are. So thanks to these relations between Sobolev norms. So what I'm going to do next is I'm going to try to answer two questions. The first one is, given a single mode subsystem of my field, how much entanglement is there between this single mode subsystem and the rest of all degrees of freedom of the field in the zeta spacetime? And the second question I'm going to try to answer is, given two space-like separated single mode subsystems, A and B, how much correlations and entanglement are there between these two? Now, to answer the first question, we can actually use the von Neumann entropy, because if this is a single mode subsystem, let's say that the entanglement, and we are considering a pure state, then the von Neumann entropy is a measure of the entanglement between this single mode subsystem and the rest of the field. So, as I mentioned earlier, the von Neumann entropy is again a function, or can be computed as a function of the symplectic eigenvalues of this single mode subsystem, which in this case is just 1 and can be written in this form. So essentially, a term that is the same we will find in Minkowski spacetime, plus a complicated functional that depends on the choice of mode and the different characteristics of this f and g, plus some subleading contributions in this regime, where the mode is supported in a region that is larger than the Hubble radius, and the mass of the field is small. Now, what is remarkable is that we can analyze what dysfunctional is or how dysfunctional behaves, and again, using these relations between Sobolev norms, we find that dysfunctional is larger or equal than 0 for all functions f and g that give rise to normalizable reduced states. So this is really nice because since the von Neumann entropy turns out to be a monotonically increasing function of its argument, in particular in this case of this new A, this is telling us that there is a larger or equal entropy in the zeta spacetime than it would be for the corresponding mode in Minkowski spacetime. So there is at least as much entanglement in Minkowski as in Minkowski spacetime. This is really nice. But this is not the end of the story, right? Because we would like to understand how much correlations and entanglement are there between two space-like separated degrees of freedom. And this is the case that we're going to analyze now. Now, if we want to understand how much correlations are there between these two single-mode subsystems, we can look at the mutual information, which again measures or gives us an idea of the total amount of correlations between A and B. So if we do that, what we find is the following. So we find that if the supports of these two modes are small compared to the Hubble radius, essentially we are in this regime, then the mutual information behaves essentially as in Minkowski spacetime. However, if we separate these two modes over distances that are larger than the Hubble radius, then we find that the mutual information reaches a plateau. So essentially, if I take two modes supported in very small regions, that would be not thinning the curvature very much, but I separate them over very huge distances larger than the Hubble radius, then I'm going to find that these two modes exhibit more correlations than they would in Minkowski spacetime. The second thing I can do to analyze the effect of the curvature on such modes is basically make the support of these modes bigger compared to the Hubble radius. And in this case, what we find is precisely this. So at some point, when the support of the modes is large compared to the Hubble radius, or at least comparable, then we find that the correlations between the two modes are essentially constant. They reach a plateau. So what this is telling us is that there are more total correlations in the zeta spacetime between 2 degrees of freedom compared to the equivalent degrees of freedom in Minkowski spacetime. However, as I've mentioned before, mutual information is a measure of total correlations. It is not a measure of entanglement. So the next thing we wanted to do was to try to understand what is the subset of these correlations that is due to entanglement. And as I mentioned, we do this using the logarithmic negativity. So interestingly, what we found is that, again, using these techniques and the relations between different Sobolev norms, that the entanglement, the logarithmic negativity between two single-mode subsystems, space-like separated in the zeta spacetime, is always smaller or equal to the logarithmic negativity between the corresponding two modes in Minkowski spacetime. And, well, of course, in the limit that we are considering. So basically, when the support of the modes is large compared to the Hubble radius, and the mass of the field is small. But this is quite surprising, right? This is telling us that there is less entanglement between local observables in the zeta spacetime when compared to the equivalent quantities in Minkowski spacetime. So, to summarize, we have analyzed, or I've tried to answer 2 questions. The first one is, how much entanglement is there between a single mode subsystem and the rest of the field, both in Minkowski and the zeta spacetime? And what I found is that necessarily in the zeta there is at least as much entanglement between a mode and the rest of the field as for the corresponding mode in Minkowski spacetime. Remember that we did this using the logarithmic the von Neumann entropy. But then we ask a second question, which is how much correlations and how much entanglement is there between two localized space-like separated degrees of freedom, both in Minkowski and de Sitter spacetime? And there the answer we found is completely different. Essentially, we found that in de Sitter spacetime there is less entanglement between local observables when compared to the equivalent observables in Minkowski spacetime. Now, well, this seems to be intention, right? But when you look at the literature, what you find surprisingly is that this kind of different results are also found in the literature, just using different techniques. For example, if you analyze the entanglement harvesting results, what you will find is that, well, two unrudebit detectors are able to harvest or extract less entanglement from the Davies vacuum than they would or than they can in the Minkowski vacuum. In other words, harvesting is smaller in de Sitter than in Minkowski. However, if you look at some of the entanglement entropy results, which essentially tell you how much entanglement is there between subsystem A containing all degrees of freedom here and its complement, well, you would find that this is entanglement, that this is larger in de Sitter spacetime than it is in Minkowski spacetime. So the question we would like to answer now is, well, is this a contradiction? Or why is this the case? And the way we can answer this is by attempting or by addressing another question. In particular, well, where is the entanglement localized? How is it distributed? In order to do this, we need, or I'm going to use a different tool, which is the notion of partner systems in a pure state. So, strictly speaking, given a single mode subsystem A, its partner in a given state or reduced state is the other subsystem in the field that encodes all the entanglement with A. Now we can also show, and this is kind of interesting, that if A is a single mode subsystem, then its partner is also a single mode of the field. You can see, you can read more about partner of pure states in these references and also in a reference that we are preparing. Now, we can also define partners for mixed states, which is also an interesting topic, because in this case, it turns out that the notion of partners divides into two subsets. So we have the notion of correlation partner, which essentially is the subsystem that encodes all possible correlations with a given system, and the notion of entanglement partners, which encode all the entanglement with a given subsystem. And while for pure states these two are the same, it turns out that for mixed Gaussian states these two are different. However, this is not needed in this talk, so I will just leave you here a reference if you are interested in reading more about this. But going back to the notion of partner systems, what we have found is that given a subsystem A that is correlated in a pure Gaussian state, then we can describe its partner in this manner, where this J, remember, is the complex structure of the reduced state acting on subsystem A, and this here denotes the orthogonal, or projection to the symplectic complement of subsystem A. And so we can show that this is the partner of A in J in this state. Unfortunately, I don't have time for the proof, but we can discuss this later on if you're interested. So, as I was mentioning, my next objective is to try to understand better what is the distribution of entanglement between a single mode subsystem and the rest of the field. As this, as I'm going to explain, can help us understand the origin of the tension I mentioned earlier. So again, for simplicity, let's take a single mode subsystem of this form, where I'm using essentially the same function here and here. For example, I can use this function here to define my single mode subsystem. And what I'm going to find is that the way the partner behaves in flat spacetime and in the zeta spacetime is very different. In particular, the partner in the zeta spacetime turns out that it's much more spread out. In fact, it's almost scale invariant. And what this is telling us is that no local observable is going to be able to capture the whole partner, not even an approximation. Or in other words, that entanglement with the partner is acting as noise for local observables. So, in a sense, the tension that I mentioned earlier is not such tension. It's actually, let's say that the two results are related. There is less entanglement between local observables because the entanglement between a single mode and the rest of the field is much more spread out, acting as a decoherence factor for local observables. Now, why is this interesting? So again, in this talk, we discussed the distribution of entanglement in quantum field theories using a particular framework, in this case, a framework that analyzes finite dimensional observables and focuses on Gaussian states. And this framework allowed us to perform or to have a geometric description of correlations and the distribution of entanglement through the notion of partner modes. Now we apply this framework to a regime that is relevant for cosmology to resolve an apparent tension between the results obtained from entanglement harvesting and entanglement. And well, the interesting point here is again that we found that there is less entanglement in the zeta spacetime between localized observables. If you think about this, these are exactly the ones that we could in principle have access to, which means that there is, if you want, a natural, let's say, natural way in which entanglement is very much suppressed in the degrees of freedom we can access. However, this is not the end of the story, because again, this is a consequence of this higher amount of entanglement between a single degree of freedom and its partner, which is essentially much more delocalized due to the presence of curvature and the almost scale invariant structure of the zeta spacetime. And so essentially, this is why I'm saying that inflation does not create entanglement in local observables. So thank you for your attention, and if there are questions, I'll be happy to answer them.
Thank you very much, Patricia, for this very interesting and also clear talk. So do we have questions from the audience? Simply connect I mean, you can switch on your camera and speak if you have a question, or raise your hand. Oh, yes, Benito. So.
Thank you very much for this nice talk, Patricia. I was wondering, a lot of the framework that you introduced is very, let's say, canonically flavored. So you talk in terms of the symplectically smeared observables, momenta, and three field, let's say. Have you thought about a way of covariantly describing this? So let's say in space-time smearing, there should be probably an equivalent way of looking at this problem.
Yeah, thank you for the nice question. So the nice thing is that for free theories, essentially we can use this, well, there is an isometry between this covariant formalism and this canonical formalism. So we can use essentially these tools. So that's why, let's say I haven't considered that much how to do it. I mean, I'm just using this correspondence because that is where I have a symplectic structure that I can use and where I can define a covariance matrix. Now, if we wanted to try to extend this formalism to interacting theories, then it would be interesting to have, let's say, a covariant definition. The problem is that this formalism relies heavily on these structures, on the symplectic structure, on the complex structure, and so on. So it is non-trivial to extend, but it's something that I'm certainly trying to think about.
Yeah,
So maybe
thanks. I mean, there is a counterpart in, let's say, the covariant formalism to the symplectic structure, because the advanced minus retarded propagator can play the role of the symplectic of the symplectic structure, let's say covariantly, right? So there is a little bit of that structure maybe that can be used. Yeah.
maybe something we can leave for the discussion is that, as you pointed out, I mean, for interacting theory, it's even that, strictly speaking, in general, it won't be well defined to these operators phi and pi on a space-like hypersurface. But maybe we can discuss these things afterwards.
Yeah.
So, Rick, do you have a question or?
Yes. So, Patricia, thank you for the talk. Very good talk as usual. The question that I have is more like, because as I understand it, most of the studies that you've conducted there is like, if you fix one mode here, then what can you tell about it, the entanglement between this mode and I don't know, some other mode, some other regions, or things like this, right? I was just wondering whether you would expect that the results that you found for one mode would generalize if you were to consider like all of the modes of the region, you know? If somehow someone were to represent all of the degrees of freedom of one region of, say, Minkowski, de Sitter, and compare them, would you expect your results to hold in this case too?
Yeah, that's an excellent question. So first thing is that it's true that I'm talking about one mode, but it can be any mode. So basically, I'm not saying which mode it is that I'm looking at. Then that's a complicated question, because we could play this game also defining different modes in the same region, let's say. So having a finite refinement of the algebra in a region and trying to see what happens with their partners and so on. If we can do this for each modes here, or we can define partners for multi-mode subsystems, which is something that we're working on now, then I think we could use it. But again, this formalism has some limitations, and it's that we are looking at a finite subset. And there are some complications again and some subtleties that one should certainly look into before giving a definite answer.
Okay, no, I agree. And just adding to Benito's question, just adding a little bit to the thing that he said, it's so regarding using the E as a symplectic structure, yeah, Benito, you're entirely right. And actually, like, what this is doing here is basically using E, but restricted to one Cauchy surface. So it's really like, at least for free theories, right? It's exactly one-to-one. I can provide you some references later if you want, that really explicitly show the connection between the modes at a surface, or the modes within the causal diamond generated by the subregion of the surface and all this. But yeah, okay. Thank you for this.
Lajos?
Yeah, my question or problem or comment may be related either to my limited capacity to follow all the details of the formalism, or to the question of covariance. So would you first of all, I love this talk and the topics as well. Would you teach me of the way you compare two states, one in Minkowski, the other one in a curved spacetime like de Sitter? Do you mean that you choose, say, the same smearing functions, or what?
Yes, so that's
so how can I come the general sad lesson of classical general relativity, that it is not easy to compare anything that happens in two totally different spacetimes.
Yes, you're absolutely right, and this is a point that I agree. I didn't explain in detail, So here, what we are using is, well, first of all, that constant time slices in the zeta spacetime are isometric to constant time slices in Minkowski. And essentially, that the structure of the two-point function, let's say, has, that the short distance structure of the two-point function is going to be something similar to Minkowski. So when I talk about these equivalent degrees of freedom, I'm really talking about using the same smoothing functions, if you want, or the same phase-based elements. So yeah, and in that sense, this analogy works pretty well because, as I showed earlier, in the limit I'm considering, we can, well, the smear two-point function has this simple structure with different terms. And we can take the limits as, for example, as the Hubble rate, well, the inverse as h goes to 0, essentially, which is the Minkowski limit. And we have this comparison that is fair with the case in Minkowski spacetime. So in that sense, we are comparing these two.
I see. Well, thanks.
Okay, so I'm not sure whether I think that Lajos, the question was clear. Was there a follow-up from your side? There was a slight interruption.
Not from my side.
Is it fine, Lajos? That was that answer your question?
Are you asking me,
Yes.
Albert?
Yes.
Yeah, I think it is an answer if I might characterize my understanding of the answer is that that there is still no exact way to compare two reduced states or in two different spacetimes, but there is some approximation, some approximate sense which would work for us.
Yes.
Was that your answer?
Yes, essentially.
Yeah. Then I'm satisfied.
I think also she pointed out at the beginning that it's not universal at all, but in this particular case, the fact that the constant time slices are basically flat, equivalent to the flat slices of it. That also is also real line. That's what helps you say, okay, so I'm comparing two things that are separated by this distance. And it's used in that sense, the meaning of the proper distance, if I understand correctly, or defined on that space-like surface, hypersurface, which is flat in both cases.
Yeah, but Albert, is it enough to make exact map between one state in Minkowski and the other one in say the sitter, if the space like metric is flat? Is it enough to map one state on one hypersurface exactly to the other one in the other hypersurface, which belongs to to another spacetime? If these space slices are flat in both, is it enough to?
Maybe Patricia can elaborate. My understanding is that you are not mapping the states.
No, I'm not mapping the states.
You have different states in different states in different space times. And it's simply that when you want to compare this notion of entanglement or correlations between these two different local observables separated by a certain distance, that's where my understanding is that in order to have a fair comparison, you need to have an equivalent way of defining this distance, for example, between those two localized modes. But the states are different states in different space-time. I don't think you're mapping those.
No, I'm not. That's you are absolutely correct. So basically, what I'm saying is that we are being able to compare it fairly precisely because of this isometry, and also because of in the end, the short distance correlations in the 2-point function. So there is a way to connect.
Okay.
And
so
again, it was happening. But
So
we are
only-
not mapping the states.
Yeah. So only the smearing functions are the same.
Yes, exactly.
Yeah.
Only the smearing functions are the same.
And this is a legitimate choice because both metrics are flat
Exactly.
in space. Okay. Okay.
Yes.
Thank you.
Okay. Thank you for asking about this. It was a point that needed clarification. Thank you.
Do we have further questions? Maybe I can ask a question that could even kind of sort of connect with the discussion part of the. So you, when you discuss the intuitive understanding of why this entanglement between local observables was smaller, although the entanglement from a single mode to the rest was larger, and you use this notion of the partners. And so that was very nice, very clear. But then the discussion about then entanglement between two localized modes, so to speak.
Yes.
You had also found, however, that the correlations, not entanglement, between those two modes,
Yes.
that was higher. So I was
Yes.
wondering whether also some sort of intuitive understanding about that would involve this result that you didn't have time to go through, which is what happens in the case of, which would be relevant for just two modes in the spacetime where it's now a mixed state, that you explained you have this generalization to that case of mixed states of this notion of partner, and there's a distinction between entanglement partners and correlation partners. You didn't have time to go into the details of the correlation partners, but if one follow or with the results you've got for correlation partners, can one then also have some intuition on why the correlation then is higher than in flat space? Maybe this could be something for the discussion part. Perhaps we can start now with that.
Well, so that's a very interesting question too. So essentially, the intuition as to why the correlations are higher is precisely, the correlations, I think that we will agree that in the sitter we have more correlations because of this almost scale invariance of the 2-point function. This comes from there. The question is, what part of these correlations are due to entanglement and what of the part of these correlations are due to something else? In particular, as I was saying, the reduced state of any 2 degrees of freedom, in this case, localized degrees of freedom is mixed. So they can have correlations that are due to entanglement and correlations that are due to something else. So what we are finding is precisely that the total correlations is larger, but the corresponding part due to entanglement is very much reduced. And the intuition for that is precisely, again, in this case, given just by the partner of each of the modes with the rest. So the way I think it is each mode is essentially correlated and entangled with a lot of other modes. But now when we reduce the state, this entanglement becomes part of the mixture of this reduced state of a single mode. So precisely because this one is entangled with everything else, the reduced state is much more mixed. And this contributes to these total correlations.
But that, I see the point. However, I can understand that somehow contributes, but that would tell you that the von Neumann entropy of the subsystem of two modes would be higher.
Yeah, and it is higher.
So that's clear. That's clear. That I understand. That's clear. But I thought that the additional point you found was that not just the von Neumann entropy of these two modes in the sitter, but also the mutual information was higher.
It is higher.
And so that part goes a bit beyond that because it's not just, I don't know, maybe one can understand it in terms of that, but the fact that or maybe it's enough, I'm not sure. Is it enough? I mean, it's not clear, right? Because the mutual information is that you have these von Neumann entropies of the two single modes that we know and we understand it's higher, But then it's really the difference of that with respect to the joint system, and then I'm not sure whether one still has an intuition or needs further aspects to.
Yeah, I think you need a little bit more. And to be honest, I think that this analogy is kind of easier to understand what's happening, but we can also understand it, I think, in terms of these correlation partners. And the reason is these correlation partners for a mixed state turn out that they are essentially multimode. And in particular, for a field, they are essentially infinite. They contain infinitely many, how to say this? Well, no, in this case, we wouldn't be looking at the full mode. So, but essentially, this correlation partner would include a lot of modes, not just a single one.
Oh, okay.
So yes, you can also understand it in this
I
way.
see. So in some sense, I guess it comes partly maybe then from the fact that we saw that every mode was entangled to a lot in the sitter, but also crucially that the correlation partners then in the sitter are very different from the entanglement partners.
Exactly. Yes, exactly. In particular, correlation partners, even for a single mode subsystem, will be multimode, but the entanglement partner is single mode.
Yes.
Yeah.
I see. So are there further questions? Otherwise, maybe we can also continue with the discussions. I don't know, Dennis, if we want to stop the recording or we can still record the discussions.
No, I think I would stop the recording and then we can continue with discussions.
Okay, so then